All right, let's get started. So we have more of the finite element interpolation part 2 for today. And I know we have a Python lecture on Friday and we'll do some coding on Friday, but I will try to plot some things. Somebody came to office hours on Monday, Isaac, who I don't think is here. And I was explaining and then I was plotting some things and I think it made it easier to explain. So I'll try to do that. But let's go through the slides first and then I'll jump on a little bit of code. Where are we and where are we going? Just one more time so that you know the big picture of the first few weeks, at least of the course, is we started with the endpoint, actually, with this KD equals F, because it was convenient to introduce the concept of having an element, doing the assembly process from an element equation to the global system of equations, and how to deal with boundary conditions. So we started by the end by this set of equations. Then we took a step back and then we did 1 week only of this very new concept of strong form to weak form. And again, the strong form is just your classical version of a PDE. And you can think of that as the PDE version of sum of forces equals 0. So that's what we did in week 2. And then what we started doing now is this approximation of functions. So that when we put both of those together, the strong form to weak form and the approximation of functions, then we'll be able to get, again, a discrete system. So the main thing to be able to use the weak form is two things. One is just an easy way to interpolate functions. And the other one is find a good way of building those weight functions that we introduced for the weak form. So that is more or less the roadmap. A little bit on some requirements for these basis functions that allow us to do both things, do the capture the weight functions for the weak form and also allow us to interpolate any function. Technically speaking, there are two basic requirements that are called continuity and completeness. These we kind of talked about a little bit. That in the strong form, we require functions that are continuous and have continuous derivatives. For the weak form, because we do the integration by parts. So because of integration by parts, then we only require continuous functions. I don't know how to spell continuous, but and I said those are C0 functions. So these are functions that are continuous, but the derivatives can be discontinuous. Obviously, if you have more continuity, it's better, but the minimum is that the function is continuous. That's the minimum requirement. And the basic basis function or shape function that will satisfy that requirement are these hat functions. So the hat functions, these hat functions, they're called hat functions. Those are linear. They have this kink. So they are continuous, but their derivatives are discontinuous. So those are the simplest set of functions that we can use. But again, this is the minimum requirement. You can have the quadratic functions and that works, or cubic functions and that works. It's just that the minimum set of functions that will allow us to satisfy that continuity requirement are these piecewise linear functions. The other requirement is called completeness, and I'm not gonna dwell too much into it, but the main idea is we are looking for solutions when we solve the problem. The actual problem, the PDE of sum of forces equals 0 or divergence of the stress equals 0, has some exact solution that we won't be getting, but we are getting for an approximate solution out of a family of solutions. That's the whole point of the FE. When we introduce these hat functions, is basically what are all the functions that we can describe by some of these hat functions. And so you can imagine that these hat functions define basically a space in which you can look for solutions. Completeness just means that for a given polynomial degree, we can interpolate any polynomial of that degree. In a different way is if we have these hat functions, which are piecewise linear, the requirement of completeness is, can we get any line or any piecewise linear function by summing these hat functions? The answer is yes. For the quadratic shape functions that we were defining at the end of the previous lecture, the question is, can we get any parabola by summing the 3 parabolas that we defined at the end of the last lecture? The answer is yes. For the cubic, again, you will have to find some cubic polynomials, and then the question for completeness is, can we describe any cubic polynomial as a sum of those few cubic polynomials? If you do that, so if you satisfy both the continuity and the completeness, then you're guaranteed to have convergence in the finite element solution. Convergence in the sense of, as you refine the mesh, your solution stops changing. So this convergence means, we'll do that for the next Abacus lab. As you refine the mesh, solution stops changing. Again, that's just a little bit of theory. We won't really worry too much about this. This is just something for you to know. How do you get continuity? Or why do the functions that we were describing before, these Lagrange polynomials, preserve continuity? Is because they have this interpolation property that we make these n functions to be 1 at a corresponding node and 0 at the other nodes. So when we did that, that guarantees that we pass through all the points that we specify. And so at the end of the day, either linear, quadratic, or whatever it is, it will pass through all the points and it will be continuous. There won't be any gaps. Again, that's just the way this is, because we use the Lagrange polynomials. It's not the only possibility. But it's convenient because it guarantees this continuity requirement. Another one is, this is what I was saying, is can we get any polynomial? If we are using linear functions, can we get any line? If we're using quadratic functions, can we get any quadratic function? We're not gonna prove why this is the case. I don't know if the book has a derivation on this, but the main thing is, for example, again, that if you use Lagrange polynomials, then this is true. Yes, then we introduced the quadratic element at the end of last week. These are the 3 shape functions. The general way of making the Lagrange polynomials is you multiply all the terms where you want it to be 0, and then this is from Wikipedia, and then you divide by the corresponding normalizing factor so that you get 1 at the desired location. And that's it. That's how we defined the linear and quadratic. Cubic, we're not going to do the cubic, but you can do cubic, quartic. In practice, what do you see in finite element codes? Linear and quadratic. That's really what you use. You don't really use high degree polynomials. So it's really mostly about linear and quadratic. Any questions so far? No? Okay, so we have no questions. I will try to share here and stop sharing here. But I'll keep on recording from. This is the experiment. Let's see if this works. One sec. Let me find the tab. There we go. This is the best way of doing it. Should I plug? The thing is, I'm recording on the iPad. I think this is the way I should do it. We'll see. I just want to plug some things. We're gonna. You are going to work on this on Friday, but I thought this was a good way of explaining things. So. What are the things that I want to show? How does this interpolation of functions work? I might go back to the notes, but for the quadratic polynomials, there's 3 of them, and they are functions of x. The reason why I like it with the code. Hopefully this is more understandable, right, Isaac? Does this make it makes it easier, right? Hopefully. These are functions of x. The thing that we defined last time, these quadratic polynomials are functions of x. So I should be able to define some function of x. And then I'll return the value. If I get x, I will return the value. Now, in reality, I also need the information about the coordinates of the element. So I'm going to pass some parameters. This is just, which are basically just the location of the coordinates of the element. But these are just parameters. These are not functional values. These are the coordinates of the element. And then it's really just a function of x. What is the quadratic polynomial? Again, I need it to be 0 for the first one. I need it to be 0 at the second node, and I need it to be 0 at the third node, right? So this product guarantees that it's 0 at those 2, and then I just need to normalize, right? So if I divide by this product, I'm just putting, instead of x, x1e and x1e. Now I guarantee that not only it's 0 at x2e and x3, but now it will be 1 when x equals x1e. That's one. Easy to just copy. And I'll post this as lecture 7 material, and then we'll do more of this on Friday. So the second shape function should be 0 at x1 and x3, and then just normalizing so that it's 1 at x2, and the third one should be again 0 at x1 and x2, and then I just normalize. There we go. All right, so I define functions, and again, these are functions. So given that I have some elements, and we can just randomly say x1e, x2e3, x3e4. Instead of having elements that has these coordinates, I'm just gonna save it in. I don't know how I call it. Let's call it node xe. So x1e, x2e, x3e. I can evaluate these functions, right? So these are functions I can evaluate at whatever value of x, well, between 2 and 4. So if I have, let's say, 2.5, right? So it will evaluate the first function at that value of 2.5. And then I could do that for the second function or for the third function. So really, I can put anything here. So let's plot it for a bunch of x's in between the 2 and 4. So what I'm just gonna do is I'm gonna create a vector of x's using, I don't know if I use this time, between 2 and 4, and let's say I want 50 points. So this x vec will create basically a vector with 50 positions of x between 2 and 4, and I can use that to evaluate my function and plot. So I'm just gonna plot that. So I'm gonna plot over x, I'm gonna plot n1e of x, and then node x. If I do that, this is wrong. Why? Because there's no vex, it's vec. So for example, this is the first parabola. And again, you can see that it goes from 1 at 2, and then it passes through 0 at 3 and 4. And then similarly, I could plot the other two. Expect node x, and let me just change the color. Right, so these are the three parabolas. Now for the interpolation part, for which I will go briefly to let me go back to the notes, and I'll go back to the. So why do we care about? I don't know here. Why do I care about this? Use shape functions. So the main idea of introducing these shape functions is that given for the quadratic element, I have the coordinates x1e, x2e, x3e, and I have my three shape functions, right? So I have this, I have, I forgot which colors I used, but I have these functions, right? So these are n1, n2, and n3. But now I want to interpolate any function by just giving 3 extra values. I'm just gonna say, I wanna give some values, and this can be whatever we want. And these are just 3 numbers. And the idea is that based on those 3 numbers and the functions, which are actually functions of x, I will interpolate I will create this UH, which is a function of X, but it's a function of X because of the shape function. So this is going to be a sum of Ni of X times UI E. So when I do that sum, I will be interpolating this function. That's what the UH is going to give me. And as I change this U1, U2, U3, I will be interpolating different functions. Yes.
Is the E exponent like a remote?
Oh, no, it's just to denote that these are for a given element.
Oh.
And it's just because, you know, this is true for if I have one element, that element has coordinates x1, x2, and x3, but those belong to that element. So for the example that we're doing right now in the code, that element has coordinates 2, 3, 4. But for another element, maybe the points are 0, 1, 2. But I still want to use x1, x2, and x3. So it's just x1, x2, and x3 for that element. Any other question? Yes.
What happens when you have 4 elements where they overlap? Would they make a continuous line that they both agree? So it only takes 3 minutes to calculate.
Oh, so you would not have, so for that, if you were to use quadratic elements, you don't overlap. So you would do, so for quadratic elements, for quadratic element mesh, you would have, let's say, and typically that's why I'm using the sort of filled in node and the empty node. This would be element 1. And this would be, so there's no overlap. This would be element 2. And so on. Yeah, that's a good point. Any other question? All right, so let me stop sharing here. Share the other one. So let me share here. All right, so now, in addition to the shape functions, I need to define this U of the, again, these are 3 numbers that basically are gonna be sort of dials that I can use to move around the interpolation. So these are 3 random numbers for now, 4, 6, 2, for example. And then what I'm gonna do is first, I'm just gonna replot the thing that I had here, plus I'm gonna scatter these other points. So I'm gonna repeat the functions, but I'm also gonna do a scatter of node X with UE. So these are the 3 functions that they look a little bit squashed because now my y-axis is a little bit bigger. And these are the 3 values of the nodal U that I have. And then what I said is that to interpolate between them, my UH is going to be, I'm gonna call it UH spec because I'm just evaluating it, is gonna be the sum of the Ni times, so the definition of UH is sum of Ni of X times the UI, right? And I'm not gonna create a function, I'm just gonna be evaluating it by evaluating this N1E at all the X locations. Times U1E, which is UE0, plus the second shape function, and 2E evaluated at those X points, times the second location, plus the third shape function, times the third location. So again, all I'm doing is I'm doing that sum at all those x points that I define with xspec. So if I plot that, what you will see is, so I'm gonna still plot the same three things that I had before, but now I'm also gonna plot for those x's, I'm gonna plot that UH vec. Let me do black. So now you see, I had three functions and 3 points, and the sum of the functions scaled by these 3 points is a new function that is quadratic and that passes through those 3 points. If I change the UE, I will get a different function. So let's choose a different UE. If I choose UE to be whatever, 3, 4, 5, and I use those UE now, then I'm gonna repeat this, but I keep on plotting things. I'm gonna keep plotting the first one, but I'm also gonna plot now a second one. Let me call it UHB2. It's the same shape functions, exactly the same, but now I'm gonna use these other 2 values. I'm gonna scatter them as well. So here I'm gonna scatter both the UE, the original ones, and now the new ones with a different color. Let's use gray. And then I'm still gonna plot the original one, but I'm also gonna plot now this new one, also in gray. Where did I? This should have been. What? Oh, times. There we go. So again, the only thing that I changed between the previous one and this plot is that now instead of these 3 black points that I have, I also have these 3 gray points. The shape functions are the same. And by doing just the sum of these 3 values times the same shape functions, now I get a function that passes through these gray points. And you can see that it's aligned. So the functions are continuous and they describe basically any parabola, even any, because 3 points describe a parabola, any 3 points that I pick, it will find whatever parabola passes through those 3 points. Obviously, for 3 points that are in a line, then the parabola is actually aligned. Any questions? Cool. About the doing it with 2 elements, you can do 2 elements. So let's say that we have another node x2. 0, 1, 2. So it's another element that is given by those 3 coordinates. The last plot. So let me just do another lint space from 0 to 2, another 50 of this. I'll repeat the colors. I will plot again this, but 2 times. X, what is this? X2 back, X2 back, X2 back. So these should plot the shape functions, but over the 0 to 2, and then the same, but over the 2 to 4. Oh, this is not correct. because I should pass here node x2. Well, there we go. So these are the n1 appears twice, but now over, and the error that I was making is I wasn't passing the correct nodal coordinates. So you can see there's two n1s, there's two n2s, there's two n3s, because now it's done for element 1 and for element 2. And you can see that you could automate this if you have a for loop and you loop over the elements, and then for every element you know what are the x1, x2, and x3. You can just call the same functions. And last thing I'll do before I ask you to do something is to plot the interpolate a function over the two elements. I will need the same thing as before, but I need to do it twice, right? So I need to do this thing that I did here. Let me do it here. One extra here. Let's say UH1. So that's going to be plotted over the first element. These are the, and then I need to know what these values should be. And then this one is x2, not x2, x2, not x2. And then the other one is UH-vec, just call it 2. This one stays the same. Now I need to know what to do with these u's. So we'll change that a little bit. So let's do U1E. There's one thing that you do need to be careful with. I'm going to see how we take care of that. So 3 random numbers.
45, 23, 38.
What was the second one? 23. Okay, so now these are the nodal values for the first element. I shouldn't call them. I'll call it UE1 and UE2 for probably it's not super confusing. Now for the second element, here's where you need to be careful, because I need 3 numbers, but the first one has to be the same as, they do share a node. There's no overlap, but they do share a node. So the first value that I need for the second element should be the same as the other one. We'll find a way of doing that automatically. But for now, I'm doing it manually. Another number. 12. One more. 20. All right. So I'm just going to use here UE1, UE1, UE1. And here I'm just going to use UE2, UE2, and UE2. And again, these are just 5 numbers. And then the shape function is the same thing that I defined at the beginning. I just evaluated different x values. And then I'm just going to plot just the same as before. So these are all the functions, all the shape functions. And then the other thing that I need to plot is over x1, x2 vec. I shouldn't call it x2 vec, it is for element 1, but anyways. UH1 vec. I'm going to plot them all in black. So that's going to plot it over the first element, and x vec over UH2 vec is going to plot the rest of the function over the second element. And again, they are obtained by just summing the shape functions times the nodal values. So it's the sum of 2 parabolas. Now, the functions are quadratic inside of each element, but they have a kink in between elements. But that's okay. All we require from these functions is that they are quadratic inside of each element, as long as they are at least continuous. This is why we do need to repeat the 38. If I don't repeat the 38, then they will not be continuous. If this is, say, 20, then I would get a gap, right? So this would be bad, because that function is not continuous. There's some jump there. So as long as I make sure that the nodal values, those can and should be shared between elements, just not overlap in terms of the elements. Any questions? right, I'll stop sharing there. I'll share here. There's one thing that I want you to work in pairs or do by yourself, and it's, I have introduced we have introduced that if you want to approximate this function of x given some nodal values, all I do is I sum the shape functions for any given x times the nodal values. What is the derivative? So I'll give you a couple of minutes to discuss with each other. I need to calculate derivatives. So I was talking with just one person, but so what is the derivative? The key thing is to know that the only thing that is a function of x are the shape functions. So the derivative is just, again, the sum over I of, the only thing that we need to take derivatives of are the shape functions, because those are the only ones that are functions of x. So for example, for linear. For linear ni, we had two. We had n1, which was x minus x2 over x1 minus x2. Therefore, the derivative of this is just minus, well, it's 1 over x1e minus x2e. and n2e, which was x minus x1e over x2e minus x1e, then the derivative of that for the linear case is just 1 over x2e minus x1e. These are constant. And then you can see that the derivative of some function u would just be the nodal values, I'll plot it in a sec, times these two derivatives. Or for the quadratic case, again, we had n1 was x minus x2, x minus x3 over x1e minus x2e, x1e minus x3e. Then the derivative of this is just sum. So x minus x3e plus x minus x2e, or the same thing in the denominator. So therefore, to take derivatives of the function u, I don't think I have time to do it, but all you need to have implemented is the shape functions and the derivatives of the shape functions. And then all you need is, again, just these three values for the quadratic case, just these three values. And given the three values, you can interpolate the function and also the derivative in the same way. It's just whether you call the n or you call the dn dx function. These are still functions of x, right? So this, obviously, well, in the case where you have a linear shape function, then the derivative is constant. So it's technically a function of x, but it's constant, so you just get a number. If the shape function is quadratic, then the derivative is a linear function, still a function of x, so you still need to pass the x value, and so on. Any question? We do have 7 minutes, so wonder what should I do? Well, I can either plot the derivative or go a little bit into how is this gonna be useful for the strong form, weak form thing. So what do you prefer? Should I plot the derivative or should I go back and talk about strong form, weak form stuff? Plotting, okay, let's do the plotting. Stop sharing. Here. Yes, otherwise it gets too dense. Let's just do. So going back to this. So for the derivative, again, the only thing that I need to implement are the derivatives. So the same way that I defined the n1, n2, and n3 above, I will have to define, actually, let me just copy that. So the same way, this was actually the only function that I defined was here. I'm gonna use the same, but I'm just gonna change to dn1 dx, dn2 dx, and dn3 dx. And then I still take in the nodal coordinates, but here it's just gonna be, this is the derivative of the first one. Very, very, very easy. This is the derivative of the second one. And this is the derivative of the third one. That's it. So this defines the derivatives of those original functions. And now I can plot, let me just use one of the ones that I used, just this one. So again, this was one set of views. The other set of views, I forgot what it was, but just gonna redefine it here and pick just some 3 random numbers. So these are nodal values. For the same element. This is the interpolation of the function. And so if I want to interpolate the derivative, if I want du h dx vec, what do I need to do? It's going to look exactly like this, exactly like that, but instead of the shape functions, the derivatives. Exactly like this, but instead of the shape functions, the derivatives, exactly like this, but just the derivatives. And that's true also for this other set of values. This is duh dx vec version 2. This is the same. This is the why is it complaining? Oh, because I didn't put a dx. It's complaining that these are not defined because this is not defined. There we go. So, and I can plot it. So these were the points. These were the. Oh wait, and I want to plot the. For those, maybe I need a different color. So I'm still gonna plot this, but I'm gonna plot du dx and du h dx vec version 2. I need a different color. I don't know. It's gonna be too many colors, purple and orange. So many things. Let me not plot things. Maybe let's hide this. I actually don't remember which one is which one, but you can see the. Let me not plot the black ones. Let me just plot the second, the line. So that makes sense, right? So this is the gray points are the values that I want to interpolate. They are on a line, so I get a line. The derivative of that line is just the slope of that line, which is slope 1. So these points were 3, 4, 5. So the slope should be 1. This orange function, it is a function, but it's constant. It's just the slope of that line. So you can, indeed, this is the correct derivative, right? So the derivative of that line is just the slope 1. And if instead I plot the other one, that one, I have no idea if it's, so if you plot this, then the black dots, the parabola, and then that purple line is the line that is the derivative of that parabola. I don't have a way of checking, but my guess is that it is correct. So sounds good. I'll see you on Friday. You'll get to do all of this coding on Friday.